There are nights when the sky does something to you. You step outside, far from the city, and the darkness above stops being background and starts being something you can feel pressing back. On a truly clear night, away from all the light pollution, away from every glow of a town or road, you might count a few thousand individual stars. To the naked eye, they seem to go on forever. An infinite scatter of light against a void that has no visible flaw. And yet, every single one of those points of light belongs to the same neighborhood. Every star you have ever seen with your own eyes, from Sirius blazing in the winter sky to the faint ones that need a moment to notice, is part of the Milky Way, our home galaxy, a city of hundreds of billions of stars, sprawled across a disk roughly 100,000 light-years wide, roughly 1,000 light-years thick, spinning slowly through space. When you see the faint smear of the Milky Way arching overhead on a dark night, you are looking at the plane of that disk from the inside. Billions of individual stars too far away to separate individually. Their combined light merging into a pale river. The Milky Way is vast enough to take the human mind some time to come to terms with. Light travels at about 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second. And it would take 100,000 years of traveling at that speed to cross the Milky Way from one edge to the other. By the time your eyes have adjusted to the dark outside on a clear night, you are looking at something that genuinely dwarfs every scale of distance that normal life ever asks us to think about. But here is the thing that stops most people cold when they first really sit with it. The Milky Way is not the universe. It is not even close to being the universe. It is a single drop in an ocean so vast that every attempt to describe it runs out of words before it runs out of space. The nearest large galaxy to the Milky Way, Andromeda, is 2.4 million light-years away. That means even our closest galactic neighbor is so far that the light currently reaching us from it left before modern humans existed on Earth, and Andromeda is practically next door. The nearest galaxy cluster of significant size is the Virgo cluster, about 65 million light-years away. The distance to the most remote galaxies yet confirmed by spectroscopy exceeds 13 billion light-years. Everything from the Milky Way's edge to that most distant confirmed galaxy constitutes the realm of what astronomers have been trying to count, and the number they arrived at with all the tools and methods accumulated over a century of effort is 2 trillion. The question of how many galaxies exist out there in the observable universe, in the total universe, now and across all of cosmic history, has haunted astronomers for a century. And the answer has changed so dramatically within living memory, not because the universe changed, but because our ability to see it improved in ways that nobody in previous generations could have imagined. And what those instruments revealed, every time they improved, was always the same message. There are more. Always more. Far more than anyone expected. More than the mind can comfortably hold. Right now, the best estimate places the number of galaxies within the observable universe at roughly 2 trillion. If you counted one galaxy every single second without stopping, without sleeping, without ever pausing for a breath, it would take you about 63,000 years to finish the count. That is longer than human civilization has existed. and that 2 trillion figure may itself be a significant overcount of the number of distinct galaxies that exist in the universe today, for reasons that grow more interesting the deeper you look into them. To understand what that number actually means, where it came from, why it keeps shifting, why it may never be perfectly precise, and what those trillions of galaxies tell us about the universe and our place within it, you have to start at the moment when human beings first discovered they had been living inside a much smaller picture than the one that actually existed. That moment is less than a century ago. In the context of modern science, which reaches back 4 centuries to Galileo and his telescope, it is almost recent. The universe's true scale was unknown to Copernicus, unknown to Newton, unknown to Einstein when he first published the general theory of relativity in 1915. It has only been within living memory, within the lifetimes of people's grandparents, that the basic structure of the cosmos became clear enough to ask the question of how many galaxies exist, and have any hope of answering it. For most of human history, the stars were the universe. Whatever lay beyond them was a philosophical question, not a scientific one. Even as telescopes improved dramatically through the 17th, 18th, and 19th centuries, and even as astronomers catalogued hundreds of fuzzy patches of light called nebulae scattered among the stars, nobody had a reliable way to measure how far those nebulae actually were. Some looked like clouds of gas, slowly luminous. Others were distinctly spiral in shape, rotating slowly like pinwheels. But their distances were unknown, and without distance, their nature was unknowable. By the early 20th century, this uncertainty had sharpened into one of the central arguments in astronomy. Astronomers had observed hundreds of these nebulae, and there were 2 serious competing interpretations of what they were. The first held that they were gas clouds and star clusters relatively close to us, all part of the Milky Way, which itself constituted the full extent of the universe. The second argued that the spiral nebulae were something entirely different, vast collections of stars comparable to the Milky Way itself, so enormously far away that even the best telescopes of the era could not resolve individual stars within them. In 1920, this argument took the form of a formal public debate at the National Academy of Sciences in Washington. Harlow Shapley, one of the most respected astronomers of his generation, defended the view that the Milky Way was everything. Heber Curtis, his opponent, argued that the spiral nebulae were distant galaxies in their own right. Both men were serious scientists making careful arguments from the limited evidence available. The debate ended without resolution because neither side had the data to prove their case. The data arrived 4 years later, from a man working night after night at the Mount Wilson Observatory in the mountains above Los Angeles. Using what was then the most powerful telescope in the world, a 100-inch reflector called the Hooker telescope. Edwin Hubble had been methodically photographing the Andromeda Nebula, one of the most prominent of the spiral patches, hunting for a specific type of variable star called a Cepheid. Cepheid variables are stars that pulse in brightness with a remarkably regular rhythm, expanding and contracting over periods of days to weeks. The key to their importance had been established a decade earlier by astronomer Henrietta Swan Leavitt. Working at the Harvard College Observatory, Leavitt discovered that there was a precise mathematical relationship between how long a Cepheid takes to complete one pulsation cycle and how intrinsically bright that star actually is. Longer period meant more luminous. This relationship turned Cepheids into cosmic yardsticks. Measure a Cepheid's pulsation period, and you know its true brightness. Compare that true brightness to how bright it appears in the sky, and you can calculate exactly how far away it is. In October 1923, Hubble found a Cepheid in the Andromeda Nebula. He was so excited that he crossed out his original notation on the glass photographic plate and wrote VAR for variable in pencil. He found more over subsequent months, eventually identifying at least 12. When he worked through the distance calculation, the answer came back in a way that made the old model of the universe simply impossible to maintain. Andromeda was roughly 900,000 light-years away. The Milky Way, even by the most generous estimates of the time, was only a few 100,000 light-years across. Andromeda was not inside the Milky Way. It was not a cloud of gas in our neighborhood. It was an entirely separate galaxy, a city of hundreds of billions of stars, existing independently at an extraordinary distance. Hubble wrote to Shapley about the discovery. When Shapley read the letter, he is said to have told a colleague, "Here is the letter that destroyed my universe." By late 1924, Hubble had made the announcement public, and the field of astronomy was transformed overnight. The Milky Way was not the universe. It was one galaxy among many. The question, now urgent, was how many? In the years that followed, Hubble and his colleague Milton Humason continued mapping these distant galaxies with the Hooker telescope, and discovered something that made the earlier revelation look almost modest by comparison. Nearly all the galaxies they observed were moving away from us. Not a few, not randomly, almost all of them, in almost every direction, were receding. And the relationship was precise. The further away a galaxy was, the faster it appeared to be moving away. This was not the galaxies themselves moving through space. It was space itself, stretching in all directions simultaneously, carrying all the galaxies apart from one another, like dots drawn on the surface of an inflating balloon. The universe was not static. It was expanding. And if it was expanding now, then running the clock backwards, it must have been denser and hotter in the past. Compressed, at some distant moment, into something impossibly small and hot. This was the first strong observational foundation for what would eventually be called the Big Bang. The implications took time to absorb even within the scientific community. Einstein had inserted a term into his equations of general relativity specifically to produce a static universe, because he assumed the universe was neither expanding nor contracting. When Hubble's observation showed the universe was expanding, Einstein reportedly called that cosmological constant his greatest blunder, though the term would return to physics decades later, reinterpreted as what we now call dark energy. The idea that the universe had a beginning, that it was not eternal and unchanging, but had emerged from a hot, dense state a finite time ago, was deeply uncomfortable to many physicists and philosophers. The phrase Big Bang was actually coined as a term of mockery by the astronomer Fred Hoyle, who preferred a competing model in which matter was continuously created to maintain a steady-state universe. The name stuck. The steady-state model did not. But what began with Hubble's discovery of Andromeda's true distance in 1924 set in motion a complete transformation in humanity's understanding of the cosmos. From a static, eternal, single galaxy universe to a dynamic, expanding, multi-trillion galaxy one, all within a single century. Knowing that other galaxies existed beyond the Milky Way was one thing. Working out how many of them there turned out to be among the most technically demanding problems in the entire history of science. The obvious approach, pointing a telescope at the sky and counting every galaxy you can see, breaks down almost immediately on contact with reality. Galaxies vary enormously in how much light they produce. The most luminous galaxies, giant ellipticals sitting at the centers of massive galaxy clusters, can be detected billions of light years away because they blaze with the combined light of hundreds of trillions of stars. But at the opposite end of the scale sit dwarf galaxies. Small, faint, barely coherent collections of a few million to a few billion stars, producing so little light that even nearby examples are difficult to detect. Many dwarf galaxies are essentially transparent to a distant observer, low-surface brightness objects that scatter their light so thinly across the sky that they blend into the background. There are also the galaxies hidden from us by geography. A significant fraction of the sky, particularly along the plane of the Milky Way, is obscured by clouds of dust and gas in our own galaxy. This region, sometimes called the zone of avoidance, blocks our view of whatever lies behind it. Some galaxies sit close together in projection on the sky and blur into each other in images. Others are so close to bright foreground objects that their light is overwhelmed. Then, there is the fundamental problem that light travels at a fixed speed, and the universe has a finite age. When you look at a galaxy 10 billion light years away, the light reaching you set out 10 billion years ago. You're seeing that galaxy as it existed when the universe was younger, denser, more actively forming stars, not as it exists right now. The present state of that galaxy is unknown to you, because the light showing its current condition has not had enough time to reach you. Some galaxies we observe no longer exist as independent structures. They have since merged into larger systems. Others that exist today have not yet sent us their light. And then there is the expansion of space. The universe is 13.8 billion years old, but the observable universe, the spherical region from which light has had enough time to reach us, is about 93 billion light years across in diameter. The difference exists because space has been expanding the entire time the light from distant galaxies was traveling toward us, carrying the sources further away. The most distant light reaching us today was emitted from points that were then much closer, but which have since been carried by cosmic expansion to locations far beyond 13.8 billion light years. The maths works out to an observable bubble about 46.5 billion light years in radius. Within that bubble, the actual process of counting galaxies requires a different strategy from simply looking at the whole sky and tallying everything visible. The approach that eventually became standard was one of deep sampling, choosing small patches of sky, observing them with the greatest possible sensitivity for the longest possible time, counting every detectable galaxy in those patches, and then scaling the result across the whole observable sphere. The logic is similar to how a field ecologist estimates the population of a vast and inaccessible rainforest. You cannot survey every tree. You choose representative plots, count and catalogue everything within them with meticulous care, and extrapolate. The quality of the final number depends entirely on how representative your sample plots are, how deeply you count within them, and how well you account for everything you couldn't detect. The organisms too small or too well hidden for your instruments to find. In astronomy, the deep sample approach required a telescope capable of detecting extraordinarily faint objects at extraordinary distances. With the patience to stare long enough for the light of distant galaxies to accumulate on the detector. For decades, no such telescope existed. The breakthrough came with an instrument launched into orbit above the blurring effects of Earth's atmosphere. Operated by scientists willing to gamble. Significant observing time on a patch of sky that appeared, to the naked eye, to contain essentially nothing. There is also a more fundamental limit that all these practical obstacles sit in front of. Even a perfect telescope with infinite sensitivity, placed in an ideal location with no foreground contamination, cannot see beyond the cosmological horizon. The most distant light that could ever reach us in principle is the light emitted at the moment of recombination. The release of the cosmic microwave background at 380,000 years after the Big Bang. Everything before that is locked behind a wall of opacity, the hot plasma of the early universe through which light could not travel. The galaxies we count live in the window between recombination and now. A window nearly 13.8 billion years deep, but bounded on both sides by physics rather than technology. The light before recombination is inaccessible, and the light from beyond the particle horizon has simply not had time to arrive. The 2 trillion figure lives within that window, and that is the most complete answer to the question that the laws of physics, as we currently understand them, will ever allow us to give. In December 1995, the Space Telescope Science Institute directed the Hubble Space Telescope to stare at a carefully selected patch of sky in the constellation Ursa Major, near the handle of the Big Dipper. The patch was tiny, roughly the size of a pinhead held at arm's length. It had been chosen for a very specific reason. It appeared to contain almost nothing. No bright stars, no known galaxies, no obvious reason to look there. Just a rectangle of sky that seemed, by every measure, as empty as sky could be. The decision to use Hubble for this was controversial. Hubble's observing time was competed for intensely by scientists with specific targets and guaranteed results. Known galaxies, planetary systems, stellar nurseries, objects that would definitely produce valuable data. Pointing the telescope at an apparently empty patch of sky for 10 consecutive days, occupying 150 of the telescope's valuable orbital passes, struck many astronomers as an unjustifiable gamble. There were scientists who actively argued against it. The proposal had the strong backing of Robert Williams, who was then the director of the Space Telescope Science Institute. He had discretionary time over a portion of Hubble's schedule, and he chose to use it for this. The observation ran from December 18th to December 28th, 1995, over the Christmas holiday, accumulating a total of more than 100 hours of exposure time across 342 separate images. When the data was processed and the final image was assembled, the scientists looking at it were confronted with something that would have been impossible to predict from looking at the raw, apparently blank sky. The image was not blank. That tiny pinhead of apparently empty darkness was packed with nearly 3,000 galaxies. Some close and bright, many of them small red smears barely resolvable, even with Hubble's extraordinary optics, representing objects whose light had been traveling toward us for 10 billion years or more, before it finally hit the camera's detector. The Hubble Deep Field, as it became known, established a principle that has shaped all subsequent thinking about galaxy counts. There are no truly empty patches of sky, at least not at the scales accessible to our best instruments. Every direction, if you look deeply enough and patiently enough, is full of galaxies. The blank spaces between the bright stars visible to the naked eye are not empty. They are simply full of things that are too faint and too distant to see without extraordinary effort. Extrapolating from that single deep image across the entire observable sky produced the first modern, instrument-based estimate of the galaxy population. Roughly 100 to 200 billion galaxies within the observable universe. It was a number that genuinely transformed public understanding of the cosmos. 100 billion galaxies. Within the span of about 70 years, the Milky Way had gone from being the entire universe to being one of 100 billion comparable structures, most of them invisible to any telescope then in regular use. But the Hubble Deep Field was itself just a beginning. The technique it established, extreme patience, tiny patches, enormous depth, was immediately extended. A second deep field was observed in 1998 in the southern sky, showing the same crowded galaxy density in the opposite direction, and confirming that the universe looks broadly the same everywhere you point. Then came the Hubble Ultra Deep Field in 2004, an exposure accumulating over 1 million seconds of integration across more than 400 orbits, reaching galaxies seen when the universe was only 400 to 800 million years old. That image contained around 10,000 galaxies in a region of sky smaller than a grain of sand held at arm's length. The cumulative Hubble Extreme Deep Field, assembled from more than 2,000 separate images taken over a decade, it extended the count further and refined it. Using that image and scaling across the full sky, the best estimate from direct counting settled at around 170 billion galaxies in the observable universe. That number became the accepted working figure through the early 2000s. The legacy of the Deep Field program extended well beyond the galaxy count. The images themselves became some of the most reproduced scientific photographs in history, and for good reason. They made visible, in a single frame, the sheer density of the universe in a way that no verbal description could match. The original Hubble Deep Field was made publicly available the same day the data was released to the scientific community, an unusual decision at the time, driven by the conviction that an image of this significance belonged to everyone. Its public release generated enormous interest and helped transform the way a generation of non-scientists thought about the scale of the cosmos. The Deep Field also drove a methodological revolution. The realization that essentially every direction in the sky yielded a comparable density of faint galaxies when observed to sufficient depth changed how astronomers designed surveys. Rather than looking for specific targets, a new generation of surveys was designed to cover large areas to uniform depth, treating the sky as a statistical sample of the universe rather than a collection of interesting individual objects. The Sloan Digital Sky Survey, the Cosmos Field Survey, the Candles Survey all descended in spirit from the Deep Fields demonstration that the faint, distant universe was not a sparse scattering of special objects, but a dense, uniform population waiting to be mapped. Then, in 2016, a team of astronomers took a fundamentally different approach to the question, and the number jumped by an order of magnitude. Christopher Consolis and his colleagues at the University of Nottingham were not simply counting galaxies in snapshots. They were building something more sophisticated. A three-dimensional picture of how galaxy number density had changed over the history of the observable universe, from the earliest times accessible to telescopes all the way to the present. The approach combined data from many different deep surveys taken at different wavelengths and different depths, then converted those images into three-dimensional maps by using the redshifts of each galaxy, the stretching of their light caused by cosmic expansion, to assign them positions in cosmic time as well as in spatial location. By comparing how many galaxies occupied a given volume of space at different epochs, the team could trace the evolution of the galaxy population across more than 13 billion years of cosmic history. It was a study that required not just counting what was visible, but building a physical model of how the visible connected to the invisible, how the galaxy population observed at different distances related to the full population that existed, including everything too faint to detect. What the analysis revealed was striking. In the early universe, particularly in the first few billion years, the same volume of space contained roughly 10 times as many galaxies as it does today. Not because 10 times as many galaxies were created and then disappeared, but because something more interesting happened. The early universe was populated by far larger numbers of small, faint, irregular proto-galaxies that subsequently merged together over cosmic time, gradually reducing the total number of distinct galaxies while building the larger structures we see in the present era. The universe's galaxy count has been in a state of slow, steady decline for most of cosmic history. Not because galaxies are being destroyed, but because they are being consolidated. The total stellar mass in the universe is broadly conserved. What changes is the number of separate containers that stellar mass is distributed across. This process of progressive merging is fundamental to understanding why the raw count from deep fields underestimates the full historical galaxy population. When Hubble and other telescopes observe the deep universe at its most extreme distances, they are seeing the universe as it was in its early phase. And that phase genuinely contained more distinct galaxies per unit volume than today. But many of those early galaxies were too small and too faint to be detected, even in the deepest fields. They showed up in theoretical models of structure formation, but not in the images. Consolis's team used mathematical models to calculate how many of those undetected small galaxies should have existed, based on what is known about how galaxy formation proceeded, and how those early dwarfs built up into larger structures. When those inferred but unobserved galaxies were added to the count, the total number of galaxies that have existed within the observable universe over all of cosmic history came to approximately 2 trillion. The announcement made headlines around the world, and understandably so. 10 times more galaxies than previously thought. 2 trillion, where there had been 200 billion. Consulas himself noted with candor that the most striking implication of the result was that more than 90% of these 2 trillion galaxies are too faint and too distant to be detected with any telescope in existence at the time of the study. Most of the universe's galaxies are, in a very direct sense, invisible to us, not because they don't exist, but because our instruments haven't yet been built that can find them. Here is an important subtlety in the 2 trillion figure that gets lost in the headline version. It counts galaxies that have existed at any point in cosmic history within the observable volume, including all those early small dwarfs that have since merged into larger systems and no longer exist as independent objects. The number of distinct galaxies in the observable universe today is much lower, probably a few hundred billion, since most of those early dwarfs have been absorbed into the larger structures that dominate the present era sky. Both numbers are legitimate answers to slightly different versions of the same question, and confusion between them accounts for a lot of muddled public discussion about what the 2 trillion actually means. To put the revision in context, the jump from 170 billion to 2 trillion was not achieved by finding new galaxies in images. It was achieved by changing the question. The older 170 billion estimate answered, how many galaxies can we detect or infer in the observable universe today? The 2 trillion estimate answered, how many distinct galaxy-scale structures have existed within the observable volume at any point across the full history of the universe? The second question produces a larger number because the early universe was more crowded with small structures, most of which have since merged and disappeared. Both questions are scientifically valid. The key is knowing which one is being answered before drawing conclusions from the number. The 2 trillion figure did not arrive out of nowhere. It is the latest step in a history of estimates that have been consistently, repeatedly, and always in the same direction wrong. In the 1920s, when Hubble had just established that other galaxies existed at all, the total known galaxy count was in the dozens. By the 1930s and 1940s, systematic cataloging programs had pushed that to hundreds of thousands. By the 1960s and 1970s, with surveys reaching greater depths, the count crept into the millions. By the 1990s, before the Hubble Deep Field, the standard estimate stood at around a few billion. Then came 100 to 200 billion. Then 2 trillion. This consistent upward march is not a sign that astronomy is unreliable. It is a sign that the universe contains a large population of objects that are genuinely difficult to detect. Faint, small, low surface brightness structures that fall below the sensitivity limits of each generation of instruments. Each time the instruments improved, those objects began appearing, and the count went up. There is a pattern here that is worth taking seriously. Each previous generation of astronomers was not being careless. They were working with the best tools available and producing the most honest estimates those tools could support. William Herschel in the 18th century catalogued around 2,500 nebulae, a monumental achievement for its time, and estimated perhaps 1,000,000 star systems in the universe. That was not a failure of intelligence. It was a reasonable extrapolation from what a ground-based telescope in the 1780s could see. A century and a half later, the first photographic surveys using glass plates extended the count to hundreds of thousands of galaxies, and the galaxies visible in those surveys looked like a reasonably complete sample, because the instruments weren't sensitive enough to reveal how much they were missing. Each generation of astronomers was, in a sense, looking at an iceberg and drawing conclusions about its total size from the tip. The galaxies that each generation missed were not hiding. They were simply too dim, too diffuse, or too distant for the available instruments to register. Low surface brightness galaxies, those that spread their stars across large areas rather than concentrating them in a bright, dense core, are a particularly good example. For most of the 20th century, these objects were almost entirely unknown. Not because they didn't exist, but because the photographic plates and early digital detectors used in surveys tended to wash them out against the general background glow of the sky. It was only when astronomers began specifically designing surveys and instruments for low surface brightness sensitivity using techniques like very long exposures, extremely dark sights, and optical designs that minimize scattered internal light, that the true abundance of these dim systems started to become apparent. There is a lesson in this pattern for interpreting the current estimate. The 2 trillion figure was derived using mathematical models to account for the undetected population, galaxies too faint and too small for even Hubble to see directly. It is not based purely on objects that have actually been observed. It requires trusting that the models correctly captured the properties of the unobserved population. If those models are wrong in the direction of predicting too many small, faint early galaxies, which the James Webb Space Telescope's observations may be suggesting, since the early universe seems to have contained fewer but larger early galaxies than the models assumed, then the 2 trillion figure may itself be an overestimate that will eventually be revised downward for the first time in the history of galaxy counting. Alternatively, better instruments may uncover populations of faint nearby objects that have been missed, extremely diffuse, low surface brightness galaxies that blend into the sky background even at relatively modest distances. Recent surveys using novel telescope designs have been finding populations of ultra-diffuse galaxies in nearby clusters that were essentially invisible to conventional instruments. These objects can be as large as the Milky Way in physical size, but contain 100 times fewer stars, spread so thinly that they register on images as barely a whisper above the background. If such objects are common across the observable universe, and early results suggest they may be, the total count could shift upward again despite any downward revision to the early universe component. The honest position, which practicing astronomers hold routinely even when headlines do not reflect it, is that 2 trillion is the best current working estimate, surrounded by uncertainties that are difficult to quantify precisely, with a strong historical precedent for revision. The universe has never yet responded to this question by offering a number smaller than the previous estimate. The direction of the error has been consistent. Whether that streak ends with the next generation of surveys, or whether it continues, is one of the genuinely open questions in observational cosmology right now. To understand where galaxies come from, it helps to go back further than galaxies themselves, to a time when the universe existed, but contained no sources of light at all. About 380,000 years after the Big Bang, the universe had cooled enough for the first atoms to form. Before that point, the universe was a dense, hot plasma, protons and electrons careering around too energetically to bond into stable atoms. The light of that era was trapped, scattered endlessly off free electrons, unable to travel freely in any direction. Then, at about 380,000 years, the temperature dropped below a critical threshold. Electrons and protons combined into neutral hydrogen atoms, and the universe abruptly became transparent. The light of that moment, stretched and cooled by billions of years of cosmic expansion into microwave radiation, is what we detect today as the cosmic microwave background, the faint afterglow of creation that fills the sky in every direction. But when that light was released and the universe became transparent for the first time, there was nothing to see. No stars, no galaxies, no light sources of any kind. The universe glowed briefly with the fading red light of its own cooling plasma, and then went dark. For hundreds of millions of years, the cosmos was a vast, featureless, lightless sea of hydrogen and helium gas, slowly cooling, slowly thickening at certain locations where density fluctuations from the earliest moments of existence were creating very slightly over-dense patches. Astronomers called this era the Cosmic Dark Ages, the period from about 380,000 years after the Big Bang until the first stars ignited. Somewhere between 100 and 250 million years later, though the exact timing remains under active investigation. During those hundreds of millions of years, no electromagnetic radiation was being generated by any astrophysical source. The universe was not just dark, it was completely dark. A darkness more total than anything that has existed in the cosmos since. The end of the Dark Ages came with the first stars, and those first stars were nothing like the Sun. Theoretical models predict they were enormous, between 30 and 300 times the mass of the Sun, in some cases possibly even larger, intensely hot, burning brilliant blue-white, and extraordinarily short-lived. Where a star like the Sun burns for billions of years, these first-generation stars burn through their fuel in a few million years at most, ending in colossal supernova explosions. During their brief lives, they blazed with enormous ultraviolet radiation, and that radiation began to do something crucial. It stripped electrons away from the neutral hydrogen atoms filling the intergalactic medium, ionizing them back into plasma. This process, the reionization of the universe's hydrogen, took hundreds of millions of years to complete. It represents one of the major transitions in cosmic history, the moment when the intergalactic medium went from neutral and opaque to ionized and transparent, and when the universe lit up with the light of its first generations of stars and proto-galaxies. The reionization era also left a direct imprint on the galaxy count. As the universe was reionized, the intense ultraviolet radiation filling the intergalactic medium began heating gas in small, dark matter halos, raising its temperature above the threshold at which it could cool and condense into stars. Small halos that might otherwise have formed galaxies were, in a sense, sterilized. Their gas heated to the point where it could no longer collapse. This process suppressed galaxy formation in the smallest structures and is one of the main physical explanations for why the number of small galaxies is lower than the raw number of small dark matter halos predicted by cosmological simulations. Understanding exactly when reionization completed, how it progressed across the universe, and which sources, the first stars, the first quasars, or the first galaxies, were responsible for the bulk of the ionizing radiation is one of the major observational goals of the James Webb Space Telescope and the next generation of radio telescopes designed to detect the 21 centimeter hydrogen line from the neutral intergalactic medium of the reionization era. One of the most remarkable indirect probes of the reionization epoch is the Gunn-Peterson trough. A near total absorption of certain ultraviolet wavelengths in the spectra of the most distant quasars discovered in the early 2000s. When quasars at extreme distances are observed, their light passes through the intergalactic medium of the early universe. If that medium still contains neutral hydrogen, which absorbs that particular wavelength of light, the quasar's spectrum shows a deep absorption feature. The discovery that quasars beyond a redshift of about 6 showed this trough, while closer quasars did not, provided the first direct evidence that the intergalactic medium had transitioned from neutral to ionized somewhere around 1 billion years after the Big Bang. That transition is the end of the Dark Ages and the beginning of the era in which the galaxy population we observe today began to take shape. The story of how these first structures formed and how the universe assembled its full population of galaxies over billions of years begins not with ordinary matter, but with invisible architecture. In the first fraction of a second after the Big Bang, quantum fluctuations imprinted tiny differences in density across the expanding universe. Some regions were infinitesimally denser than average, others infinitesimally more sparse. These variations were so small, deviations from uniformity of roughly 1 part in 100,000, that the early universe was, to any practical measurement, almost perfectly smooth. But gravity is patient, and those small differences were enough. In the ordinary matter of the early universe, density fluctuations were suppressed for a long time by the intense radiation pressure of the hot plasma. Radiation and ordinary matter were locked together, and radiation pressure fought against gravity's tendency to pull matter into concentrated clumps. But dark matter, the invisible, gravitationally active substance that makes up roughly 85% of all matter in the universe, was not subject to radiation pressure. It only felt gravity. So while ordinary matter churned in the hot plasma, dark matter was quietly beginning to aggregate, pulling into filaments and clumps and sheets, building the invisible scaffold that would eventually organize all of the visible universe. When ordinary matter finally decoupled from radiation at 380,000 years, the moment of recombination, it found dark matter scaffolding already in place. Hydrogen and helium gas flowed into the gravitational wells that dark matter had been assembling throughout the Dark Ages. And within those wells, the gas slowly cooled, condensed, and ignited into stars. The first galaxies formed at the nodes and intersections of this dark matter web, the places where multiple filaments converged and the concentration of matter was highest. This is why galaxies, even today, are not scattered randomly through space. They trace the cosmic web clustering along its filaments and congregating at its nodes, leaving the vast empty voids between the filaments almost completely devoid of structure. Each early dark matter halo that captured enough gas to ignite star formation became the seed of a galaxy. The smallest halos produced the smallest proto-galaxies. Over time, gravity brought those small structures together. They merged. Two galaxies meeting under gravity do not simply pass through each other cleanly. Stars are spaced so far apart within any galaxy that direct stellar collisions during a galactic merger are vanishingly rare, but the gravitational interaction reshapes both galaxies dramatically. Stars are flung into new orbits. Gas clouds are compressed by shock waves, triggering intense new rounds of star formation. The shapes of both original galaxies are warped and twisted. After multiple passes over hundreds of millions of years, the two systems eventually settle into a single merged structure. This bottom-up assembly, small structures merging to build larger ones, which in turn merge to build still larger ones, is the dominant process shaping the galaxy population across cosmic time. The large galaxies of the modern universe are the accumulated products of dozens or hundreds of earlier mergers, each of which brought together material that had itself been assembled through earlier rounds of merging, stretching back to those first small proto-galaxies of the reionization era. It is worth pausing on what the phrase early proto-galaxies actually means in physical terms. These were not miniature versions of the Milky Way. They were small, turbulent assemblages of young, massive stars, probably no more than a few million to a few 100 million solar masses in total, lighter than the satellite galaxies orbiting the Milky Way today. Many were not even disc-shaped. They were irregular clumps, dense with star formation activity, surrounded by clouds of gas being rapidly enriched with the heavy elements produced in the explosions of their first stellar generations. Their lifespans as independent objects were often short, a few 100 million years before they encountered a more massive neighbor and were pulled apart or absorbed. The distinction between these original small structures and the galaxies we observe today also matters for understanding the 2 trillion figure. When Conslice's team calculated that 2 trillion galaxies have existed in the observable universe across all of cosmic history, they were counting every one of those early small proto-galaxies as a distinct object, which they were briefly before being absorbed. The count includes many structures that no longer exist as independent entities, dissolved into the larger systems that dominate the present-day universe. This is why the historical total and the present-day count are such different numbers, and why both can be simultaneously true. One of the most immediate things you notice when looking at deep field images is that galaxies are not all the same. They come in a remarkable range of shapes, sizes, colors, and levels of internal activity. A diversity that reflects the enormously varied histories different structures have followed through cosmic time. When Edwin Hubble catalogued galaxies in the 1920s and 1930s, he organized them into a classification scheme based on visual appearance that is still widely used today, often depicted as a tuning fork diagram. On one branch sit elliptical galaxies, smooth, featureless, roughly egg-shaped clouds of stars with no internal structure visible, ranging from almost perfectly spherical to quite elongated. Ellipticals are typically composed of old, red stars and contain relatively little gas or dust, which means they are not actively forming many new stars. They tend to be the largest and most massive galaxies in the universe. The giants at the centers of rich galaxy clusters, some containing hundreds of trillions of stars, are almost invariably ellipticals. On the other branches sit spiral galaxies, which come in two main varieties: ordinary spirals and barred spirals. Both types have a central bulge of stars, a flat rotating disk, and arms curving outward through the disk. In barred spirals, which include the Milky Way, the central region is elongated into a bar shape, with the spiral arms beginning at the ends of the bar rather than directly from the center. Spiral galaxies typically contain a mix of old and young stars, gas and dust, and they actively form new stars in their disks. Their blue-white arms glow with the light of recently born, massive stars. Between the ellipticals and the spirals sit lenticular galaxies, a transitional type that has the disk structure of spirals but has largely exhausted its gas, leaving it with no active spiral arms and very little new star formation. And then there are the irregulars, galaxies that fit none of those categories, having been distorted by interactions with neighbors, by internal instabilities, or simply by forming in conditions that produce no clean structure. Many of the galaxies visible in deep field images are irregular or peculiar in appearance, and this is not random. The deep universe is dominated by galaxies seen at earlier cosmic times, when mergers were more frequent and the galaxy population was generally more chaotic and less organized than today. What this morphological diversity means for galaxy counts is significant. Different galaxy types have very different surface brightnesses, the amount of light they produce per unit area on the sky. Giant ellipticals are bright and compact, easy to detect at extreme distances. Low surface brightness irregulars and dwarf galaxies scatter their light thinly across the sky, making them much harder to detect and easy to miss in surveys not specifically designed to find them. The more carefully astronomers have looked for the faint end of the galaxy population, the smallest, dimmest, most diffuse structures, the more of them they have found, and the higher the total count goes. There is also the question of where to draw the line between a galaxy and something else. The boundary between a very small dwarf galaxy and a large globular cluster. A gravitationally bound sphere of hundreds of thousands of stars that orbits within a larger galaxy is genuinely blurry and has been a source of ongoing definitional debate. Globular clusters, of which the Milky Way has about 150 known examples, can contain hundreds of thousands to a few million stars and are ancient, most formed in the early universe. Some of the objects recently discovered orbiting nearby galaxies sit in an ambiguous zone, too large and too diffuse to be typical globular clusters, but too small and too simple to fit comfortably into the category of dwarf galaxy. How those borderline objects are classified affects the count, and different research teams apply different criteria. Galaxy morphology also evolves. A galaxy that is a turbulent, irregular today may, after a merger or a long period of undisturbed evolution, become an elliptical or develop a disk structure. The classification scheme is a snapshot of current appearance, not a permanent label. Deep field images capture galaxies at different stages of their evolution. The same physical object observed at different cosmological epochs, might be classified differently. This is part of what makes the galaxy count not simply a census of static objects, but a survey of a population in constant, slow transformation. Every large galaxy in the known universe, and probably most small ones too, contains at its center an object of almost incomprehensible density. A supermassive black hole. Not just a stellar mass black hole, the remnant of a single collapsed star a few times the mass of the Sun, but a black hole containing millions, hundreds of millions, or in the most extreme cases, billions of solar masses worth of material packed into a region smaller than our solar system. The Milky Way's central black hole, named Sagittarius A star, contains about 4 million solar masses and sits about 26,000 light-years from Earth. Most of the time it is quiet, not actively swallowing large amounts of material and producing relatively little radiation. But at some point in the Milky Way's past, Sagittarius A star was almost certainly far more active, drawing in gas from its surroundings and generating enormous amounts of energy in the process. When a supermassive black hole is actively feeding, it can produce more energy per second than the entire rest of the galaxy combined. Material falling toward the black hole heats up to extreme temperatures, emitting radiation across the full electromagnetic spectrum. Powerful jets of energetic particles can shoot out perpendicular to the plane of accretion at nearly the speed of light, extending thousands or even millions of light years into the surrounding space. These actively feeding black holes are called active galactic nuclei, and the most luminous versions, pouring out energy equivalent to hundreds of billions of suns, are called quasars. Quasars were first identified in the 1950s and 1960s as extremely bright, point-like radio sources at extraordinary distances. They were initially baffling. There appeared to be no known physical mechanism capable of producing that much energy from such a compact region. The explanation that eventually took hold, confirmed by decades of subsequent work, is that quasars are the hyperluminous cores of distant galaxies whose central black holes are consuming material at enormous rates. The abundance of quasars peaks at around 2 to 3 billion years after the Big Bang, the same era when galaxy mergers were most frequent and the supply of infalling gas was highest. This is not a coincidence. Galaxy mergers channel large quantities of gas toward galactic centers, fueling the feeding frenzies that power quasars. And crucially, the relationship between a galaxy and its central black hole is not simply that of a host and an embedded object. There is a precise, consistent relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central stellar bulge across many orders of magnitude in galaxy size. The black hole mass runs at roughly a fixed fraction of the bulge mass. This correlation, discovered in the late 1990s, implies that the galaxy and its black hole co-evolved, each influencing the other's growth. When the black hole feeds vigorously, the energy it injects into its surroundings can heat and expel gas from the entire galaxy, suppressing star formation and putting the brakes on the galaxy's further growth. When the black hole starves, star formation resumes. This feedback loop shapes the overall distribution of galaxy masses we observe across the universe. When astronomers talk about detecting the most distant galaxies in the universe, They rely on a property of light called redshift, a phenomenon so central to cosmological observation that it is worth understanding clearly, because it is what makes counting galaxies across cosmic time both possible and technically treacherous. Light travels as a wave. The color of visible light depends on its wavelength. Short wavelengths correspond to blue light, long wavelengths to red. When a light source is moving away from you, the waves of light get stretched out during their travel, arriving with longer wavelengths than they had when emitted. For visible light, this means the light appears shifted toward the red end of the spectrum. In an expanding universe, this cosmological redshift happens not because galaxies are physically flying through space, though some of that motion exists too, but because the space itself, through which the light is traveling, is stretching as the light travels, lengthening its wavelength in transit. The amount of stretching is directly related to how much space has expanded since the light was emitted. For a nearby galaxy whose light left it only a few 100 million years ago, the stretching is small. The light arrives nearly at its original wavelengths. For a galaxy from which light has been traveling for 13 billion years, the stretching is enormous, and light originally emitted at visible wavelengths may arrive as infrared or even microwave radiation. This is the fundamental reason why the James Webb Space Telescope is so much more capable than Hubble for probing the early universe. Hubble observes primarily invisible and near ultraviolet light. The light from a galaxy formed when the universe was only a few 100 million years old has been so thoroughly redshifted by the expansion of space that it arrives at infrared wavelengths completely outside Hubble's range. Webb's infrared instruments detect that light directly, while Hubble is essentially blind to it. Measuring redshifts accurately is observationally expensive. The most reliable method, spectroscopy, where a galaxy's light is spread into its component wavelengths and specific chemical features are identified and compared to known laboratory values, requires long observation times and large telescopes. For faint, distant galaxies, spectroscopic confirmation can take many hours per object, making it impractical to confirm more than a fraction of any given survey. The faster alternative, estimating redshifts from the shape of a galaxy's brightness across several broad wavelength filters, is much quicker but less precise, and it can occasionally place a galaxy at a completely wrong redshift when the color profile is ambiguous. Several of Webb's most exciting early reports of extremely distant galaxies turned out to have these photometric redshift errors when spectroscopic follow-up was eventually performed. The galaxies were real, but at different distances than initially suggested. This is not a failure of the science. It is the normal process of refining preliminary estimates with more precise measurements. But it illustrates the technical difficulty of working at the extreme frontier of what is observable. Redshift is also what makes the galaxy count inherently a four-dimensional problem, rather than a three-dimensional one. Because light has a finite speed, distance and time are the same thing in observational astronomy. When you measure the redshift of a galaxy and calculate that it is 10 billion light-years away, you are simultaneously learning that you are seeing it 10 billion years in the past. The galaxy population at redshift 1, roughly 8 billion light-years away, is simply a different population at a different point in cosmic history from the galaxy population at redshift 0, which is what surrounds us today. A complete census of galaxies is therefore not a map of a single moment, but a simultaneous view of many different cosmic epochs, each one showing the universe at a different stage of its development. This time-layered nature of galaxy surveys is both a complication and an extraordinary scientific advantage. It means that by comparing the properties of galaxies at different redshifts, their sizes, shapes, colors, star formation rates, and merger frequencies, astronomers can directly observe how the galaxy population has evolved, rather than having to infer it purely from theoretical models. The evolution is visible in the data, encoded in the way galaxies look different at different distances, and teasing apart the threads of that evolution is one of the central goals of modern observational cosmology. The James Webb Space Telescope launched on December 25th, 2021, and began full scientific operations in July 2022. It was the most expensive and technically complex space observatory ever built, nearly 3 decades in development, the product of an international collaboration involving NASA, the European Space Agency, and the Canadian Space Agency. Its primary mirror is 6.5 meters across, made of 18 hexagonal gold-coated beryllium segments that unfold in space like a flower. Unlike Hubble, which observed primarily in visible and ultraviolet light, Webb is an infrared telescope designed to detect the red-shifted light of the most distant, earliest galaxies, objects so far away and so old that their light has been stretched far beyond the visible spectrum, completely invisible to Hubble's detectors. Webb's first deep field images arrived in July 2022 and immediately demonstrated that the instrument was performing at or above its design specifications. Within weeks, teams of astronomers had identified dozens of candidate galaxies at extreme redshifts, objects potentially seen when the universe was just a few 100 million years old. Within months, the field was in a state of productive excitement that bordered on mild bewilderment. The issue was not just that Webb was finding very distant galaxies. It was built for that. The issue was what those galaxies look like. The early universe should, according to the theoretical models built up over decades, have contained primarily small, faint, irregular proto-galaxies, the raw seeds from which larger structures would eventually be assembled. What Webb was finding, instead, was a significant number of surprisingly massive, surprisingly luminous, surprisingly structured galaxies at unexpectedly early times. In 2023, a team led by Erica Nelson at the University of Colorado Boulder published a study describing 6 galaxies observed by Webb from within the first 700 million years of cosmic history, each containing stellar masses that existing models simply did not predict should be possible so early. Nelson described the findings memorably. "It's bananas," she said. The galaxies were, by the model's predictions, too large, too early, too mature. They represented either a significant challenge to the standard framework of galaxy formation or, more likely, evidence that the processes driving early galaxy growth operate faster and more efficiently than theorists had assumed. The most distant confirmed galaxy known as of mid-2024 is JADES-GS-Z14-0, detected by Webb's near-infrared spectrograph during the JWST Advanced Deep Extragalactic Survey program. Spectroscopic observations confirmed it at a redshift, placing its light's departure at approximately 290 million years after the Big Bang, just over 2% of the current age of the cosmos. The galaxy is over 1,600 light-years across and blazing with the light of young stars. Its infrared spectrum also revealed the presence of oxygen, a heavy element that can only be forged inside stars and dispersed by supernova explosions. The presence of detectable oxygen at this early date means that at least one full generation of massive stars had already been born, lived, and died before this galaxy was observed. The timeline is very tight, and the finding continues to challenge models of how quickly the first galaxies could have assembled and evolved. Webb's early universe discoveries connect to a broader story about how the universe's productivity has varied across time, because the rate at which the universe has been building new stars has not been constant. It has followed a dramatic arc with a peak, a long decline, and an eventual end. If you could track the total rate of new star formation across every galaxy in the observable universe simultaneously, a kind of cosmic birth rate, you would find it rising steeply through the first few billion years of cosmic history, reaching a peak somewhere around 2 to 4 billion years after the Big Bang, and then declining continuously from that point forward to the present day. Astronomers call the era of peak star formation cosmic noon, a time when the universe was building its stars at a rate roughly 10 times higher than today. The galaxies of the cosmic noon era were often spectacular. They were gas-rich, turbulent, frequently involved in mergers, and converting that gas into stars at furious rates. Many were irregular in shape, chaotic with star-forming regions blazing blue-white. Some were starburst galaxies in which star formation was so intense that the available gas supply would have been exhausted in a few tens of millions of years if maintained, driven by mergers that compressed enormous quantities of gas simultaneously. The peak of quasar activity coincided roughly with this era, since abundant merging also funneled gas toward galactic centers, feeding the supermassive black holes there. This era of cosmic productivity is also directly connected to the galaxy count. The merger rate was highest at cosmic noon, meaning the count of distinct galaxies was declining most rapidly at exactly the same time the universe was most luminous and most active. Stars were being built at peak rates even as the number of separate galaxies was falling, because mergers were consolidating gas supplies from multiple systems into single star-forming regions more efficiently than any one isolated galaxy could manage. The productivity of the universe and the reduction of its galaxy count were, at cosmic noon, two aspects of the same process. One of the most useful traces of cosmic noon is a type of galaxy called a sub-millimeter galaxy, a class of intensely star-forming objects that are almost invisible in visible light, because the same dust clouds that trigger their star formation also absorb the resulting starlight, re-radiating it in the far infrared. These objects, discovered in large numbers in the late 1990s using specialist radio and sub-millimeter telescopes, are some of the most vigorously star-forming systems ever found, converting the equivalent of hundreds or thousands of solar masses of gas into new stars every year. Most of them are seen at the distances corresponding to cosmic noon, and their abundance at that epoch and scarcity today is one of the clearest illustrations of how dramatically the universe's star-forming character has changed. After cosmic noon, the universe entered what might be called the long afternoon, the current epoch in which star formation continues, but at a diminishing pace, as the cold gas supply that galaxies need to build new stars is gradually consumed, heated by feedback from black holes and dying stars, or dispersed into the surrounding intergalactic medium. The stars being born today are joining a population that already contains most of the stars that will ever exist in this part of the universe. The Milky Way's current star formation rate is modest, perhaps a few solar masses worth of new stars per year across the entire galaxy. Compared to the hundreds or thousands of solar masses per year that characterize the most active galaxies of the cosmic noon era. The universe's supply of raw hydrogen gas is finite and being gradually depleted. At some point in the distant future, the last generation of stars will form from the last available cold gas, and no new stars will be born anywhere in the observable universe. The existing stars will continue to shine. The longest-lived red dwarfs will burn for trillions of years. But the great era of stellar productivity is already well past its peak. And the trajectory is one of gradual and irreversible dimming. Galaxies are not scattered through space randomly, like dust sprayed into a room. They inhabit a vast and intricate structure that spans the entire observable universe. An architecture so large that it took decades of surveys to map even a small fraction of it, and so complex that understanding why it has the form it does requires reaching back to the physics of the universe's first second. The structure is called the cosmic web, and the name is well chosen. At the largest scales accessible to galaxy surveys, the distribution of galaxies looks like a three-dimensional network of filaments. Threads of matter hundreds of millions of light years long, connected at dense nodes where galaxy clusters containing hundreds or thousands of individual galaxies congregate. Between the filaments and nodes lie vast, nearly empty regions called cosmic voids, some of them stretching hundreds of millions of light years across, containing only a tiny fraction of the galaxy density found in the filaments. The web was not arbitrarily assembled. It is the direct descendant of the density fluctuations imprinted in the early universe and amplified by dark matter's gravitational influence over 13 billion years. Dark matter formed the invisible skeleton of the web first. Ordinary matter, gas, and eventually stars and galaxies followed the dark matter into its gravitational wells, lighting up the web's structure in the traces that telescopes can detect. The Milky Way sits on the outskirts of the Virgo cluster, a massive congregation of more than 1,300 galaxies, about 65 million light-years away, which in turn sits within a larger region called the Laniakea supercluster, identified and named in 2014. Laniakea spans roughly 500 million light-years and encompasses around 100,000 galaxies. It is not a gravitationally bound object. Its outer regions are being pulled apart by cosmic expansion. But it represents a region of common gravitational flow. All its member galaxies streaming in roughly the same direction under the influence of a concentration of mass sometimes called the Great Attractor. Beyond Laniakea, the web continues to scales that challenge description. The Sloan Great Wall, discovered in 2003, stretched approximately 1 billion light-years in length. In 2025, astronomers announced a new candidate for the largest known structure in the observable universe, informally named Quipu, a filamentary superstructure potentially spanning multiple billions of light years, identified through analysis of large galaxy surveys. The voids are in some ways just as important scientifically as the filaments. The Boötes void extends roughly 330 million light-years across. In a region of that size with average galaxy density, you would expect hundreds of galaxies. The Boötes void contains only about 60. These enormous underdense regions were left behind as matter drained gravitationally away toward the denser filaments and nodes. A slow cosmic drainage process still continuing today. Within voids, the few galaxies that remain tend to be smaller and bluer than average, evolving in relative isolation, unaffected by the environmental pressures of dense clusters. There is also an important sense in which the cosmic web tells us something about the galaxy count that raw numbers alone cannot convey. The 2 trillion are not distributed randomly or uniformly. If you were to pick a random point in the observable universe and ask how many galaxies were within, say, 100 million light years, the answer would depend entirely on whether you landed in a filament, a cluster, a void, or somewhere on the diffuse outskirts of a supercluster. The local density can vary by many orders of magnitude depending on location within the web. The 2 trillion is a total, not an average that applies equally everywhere. This non-uniformity is itself a source of information. The statistics of how density varies from place to place, what cosmologists call the matter power spectrum, encode the physics of the early universe, the properties of dark matter, and the influence of dark energy on structure growth over time. Future surveys that map the galaxy distribution to greater depth and precision are not just counting galaxies, they are measuring the shape of the cosmic web at different scales, and using that shape to test and constrain the physical models that predict it. Every additional galaxy in the catalog is a data point contributing to that measurement. Every galaxy we count is, in a sense, the luminous tip of a much larger dark matter halo. An invisible sphere of dark matter extending far beyond the visible stars. Sometimes out to distances many times the diameter of the galaxy's luminous disk. The dark matter halo is what holds the galaxy together. Stars in the outer regions of a spiral galaxy's disk are moving so fast that without the additional gravitational pull of an extended dark matter halo, they would fly off into intergalactic space. The halo provides the extra mass needed to explain the observed orbital speeds, a problem Vera Rubin and her colleagues identified and documented in detail during the 1970s and 1980s, measuring the rotation curves of dozens of spiral galaxies and finding the same anomaly in all of them. But not all dark matter halos contain galaxies. The smallest halos, those below a certain mass threshold, apparently never accumulated enough ordinary matter to form stars at all. Or if they did form a small number of stars initially, the intense ultraviolet radiation from the first generation of massive nearby stars drove their gas away before much star formation could occur, leaving them as dark, starless halos, invisible structures of dark matter containing no luminous matter whatsoever, drifting through the universe undetectable by any telescope we have ever built. The number of these dark, starless halos in the observable universe is predicted by cosmological simulations to be enormous, possibly comparable to or larger than the number of luminous galaxies. Computer simulations of cosmic structure formation, when run with sufficient resolution to model small-scale structure, consistently produce far more small dark matter halos than there are corresponding small galaxies. This discrepancy, known as the missing satellites problem, has been a central challenge for galaxy formation theory for more than 2 decades. Part of the resolution has come from observations. Wide-field surveys of the sky around the Milky Way have revealed a growing population of extremely faint satellite galaxies orbiting our own galaxy, objects too dim to have been seen in earlier surveys, bringing the known count of Milky Way satellites from a handful to several dozen, with more being found regularly. Similar campaigns around Andromeda have turned up comparably faint companions. If these very faint dwarf galaxies are typical of large galaxy environments across the universe, then the total luminous galaxy count is probably higher than estimates based on older, less sensitive surveys would suggest. But the gap between predicted dark matter halos and observed luminous galaxies is still not fully closed by finding more faint satellites. Physical processes that suppress star formation in small halos, reionization heating, which fills the intergalactic medium with ultraviolet radiation from the first stars and prevents gas in small halos from cooling and condensing. Supernova feedback, which can expel gas from shallow gravitational wells, and tidal stripping by larger neighbors, which can remove a small galaxy's gas supply entirely, all contribute to leaving some halos permanently dark. Understanding exactly where the threshold lies between halos that make galaxies and halos that don't is one of the active frontiers in galaxy formation research, and the answer has direct implications for the total galaxy count. The dark matter architecture of the universe also shapes the cosmic web in ways the luminous galaxy distribution only partially reflects. The full web of dark matter filaments is smoother and more continuous than the galaxy distribution, because galaxies are concentrated at the densest nodes, while the filaments connecting them contain dark matter, but relatively few luminous objects. If we could somehow map the dark matter directly, and next-generation gravitational lensing surveys are designed to probe its distribution more precisely, the cosmic web would appear far more richly detailed and intricately connected than even the most comprehensive galaxy surveys suggest. The 2 trillion galaxies we count are the lit windows of a much larger structure, most of which remains permanently invisible. The galaxy count is not static. The universe itself is progressively reducing the number of distinct galaxies through the ongoing process of mergers and collisions. The same process responsible for building the large galaxies we see today from the smaller proto-galaxies of the early universe. When 2 galaxies of comparable size meet under gravity, neither is simply destroyed. Stars within a galaxy are so far apart that even as 2 galaxies pass through each other, direct stellar collisions are vanishingly rare. What happens instead is a gravitational ballet playing out over hundreds of millions of years. As the 2 galaxies approach, their mutual gravity distorts both structures, pulling long tidal tails of stars away from each system. They pass through each other, slow, and return. Each pass exchanges orbital energy and momentum, drawing the 2 systems closer. Eventually, after multiple passes and billions of years, the two galaxies settle into a single merged structure. The outcome of a major merger between two spirals is typically an elliptical galaxy. The organized rotation of both original disk galaxies is scrambled by the gravitational interaction, and stars end up on randomized orbits rather than the orderly circular paths that characterize a spiral disk. The merger also compresses gas, triggering intense bursts of star formation that can temporarily make the merging system blaze far more brightly than either galaxy did individually. And if either galaxy's central black hole is feeding at the time, the encounter can trigger a quasar phase, briefly making the merging system one of the most luminous objects in the observable universe. Some of the most spectacular objects in the nearby sky are galaxies caught mid-merger. The Antennae galaxies, two spirals in the process of combining roughly 60 million light-years away in the constellation Corvus, show exactly what this looks like. Long tidal tails of stars stretching away from both systems, a chaotic central collision zone blazing with newly triggered star formation, and dust lanes visible even in modest telescopes. What looks violent at a human timescale is, on the scale of galaxy evolution, a normal and fundamental process of assembly. When a large galaxy absorbs a much smaller one, the smaller galaxy is torn apart by tidal forces long before the merger completes. Its stars are stripped into long streams that wrap around the larger galaxy before being gradually absorbed. This process is ongoing in the Milky Way right now. The Sagittarius dwarf galaxy has been in the process of being torn apart and absorbed for billions of years, its stars forming long ribbons detectable in the positions and motions of individual stars across the sky. Several other streams of stars in the Milky Way's outer halo are the remnants of earlier companions that have already been fully dissolved. Ghost trails of galaxies that no longer exist as independent structures. The Milky Way and Andromeda are themselves on a collision course. Andromeda is currently about 2.4 million light-years away and approaching at roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies will begin to interact. The full merger will take several billion years of passes and tidal reshaping before settling into a single structure. An eventual elliptical that astronomers have nicknamed Milkomeda. Whether the solar system survives in roughly its current configuration is uncertain. The gravitational reshuffling of a galactic merger could fling the Sun to a very different region of the resulting galaxy, though the chances of any individual stellar collision during the process remain negligibly low. Each merger reduces the count of distinct galaxies by at least one. The slow historical decline in the total number of galaxies, from 2 trillion down to the few 100 billion distinct structures that exist today, continues at this pace, and will continue until the local group itself eventually consolidates into a single, merged remnant billions of years from now. The 2 trillion figure is bounded. It refers to the observable universe, the region from which light has had enough time to reach us since the Big Bang. But the universe does not end at that boundary. The boundary is not a physical edge, but an informational one, a wall created by the finite speed of light and the finite age of the universe. Beyond the observable horizon, the universe almost certainly continues. Inflationary models of the early universe, which propose that the cosmos underwent a brief period of exponentially rapid expansion in its first fraction of a second, imply that the total universe is vastly larger than the part we can see. During inflation, quantum fluctuations were stretched to cosmic scales, and any pre-existing structure was smoothed away, leaving behind a vast, nearly uniform sea of space, far larger than the small region that would eventually become our observable universe. The region that expanded to become everything we can observe was, during the inflationary epoch, an almost infinitesimally small fraction of the total inflated volume. Some estimates place the total volume of the post-inflationary universe at least 10 to the 23rd power times larger than the observable portion. If so, and if galaxy density across the whole universe is broadly similar to what we observe locally, the total number of galaxies in the universe, observable and unobservable combined, would be a number so large it becomes effectively meaningless to express as a quantity. It would be, for any practical purpose, infinite. There is a further complication in interpreting that figure. The cosmological principle, the assumption that the universe looks broadly the same everywhere, is well supported within the observable volume, but cannot be tested beyond it. If the universe beyond our horizon is genuinely similar to what we can see, then scaling the local galaxy density to the whole universe is a reasonable exercise. But if inflation produced a universe with genuinely different physical conditions in different regions, different constants, different vacuum energies, different cosmological parameters, then no such scaling is valid. We simply have no way to know. The total galaxy count for the universe as a whole is therefore not just uncertain, but potentially unknowable in principle. Even within the observable universe, the horizon is changing over time, and not in the direction you might expect. Dark energy is causing the expansion of the universe to accelerate. This means that galaxies currently near the outer edge of our observable region are being carried away from us at increasing speeds. There are two relevant boundaries here. The particle horizon, which defines the observable universe, currently about 46.5 billion light-years in radius, and the event horizon, which defines the maximum distance from which any signal sent today could ever reach us in the future. The event horizon is smaller than the particle horizon, and is shrinking over time as the expansion accelerates. Galaxies that are currently visible will eventually cross that threshold, and their future light will never reach us again. Not because they stop emitting, but because the space between us and them is growing faster than light can traverse it. The observable universe will, over very long timescales, not become richer in visible content but progressively poorer. Galaxies will recede across a one-way threshold, and the universe accessible to any future observers will be emptier than the one we inhabit today. There is a puzzle that has existed since at least the 19th century, and understanding why it is a puzzle illuminates something profound about galaxy counts and the structure of the observable universe. If the universe were infinite in extent, and if galaxies and stars were distributed throughout that infinite space, then no matter which direction you looked in the night sky, your line of sight would eventually hit a star. Every point in the sky should be as bright as the surface of a star. The night sky should blaze with light. Instead, it is dark, overwhelmingly dark, with only sparse pinpoints of light visible. Why? This question is called Olbers paradox, after the astronomer Heinrich Olbers, who popularized it in the 19th century. The resolution turns out to require exactly the facts about the universe that astronomers spent most of the 20th century establishing. The universe is not infinite in the relevant sense. It has a finite age, 13.8 billion years, which means that light from beyond a certain distance has not had time to reach us. Beyond the cosmological horizon, there may be stars and galaxies in enormous numbers, but their light has not arrived yet. The darkness of the night sky is a direct consequence of the universe's finite age and the finite speed of light. If the universe were infinitely old, the sky would indeed blaze. There is also the expansion of the universe to consider. Even for the light that has had time to reach us from distant galaxies, that expansion has stretched it to longer and longer wavelengths, reducing its energy. Light from the most distant sources arrives, stretched into infrared and microwave wavelengths, rather than adding to the visible brightness of the sky. Every time you step outside on a clear night and notice that the space between the stars is dark rather than bright, you are, without necessarily realizing it, observing evidence for the Big Bang and the finite age of the universe. The night sky tells you, simply by being dark, that the universe did not exist forever. Astronomers have measured the total light from all galaxies in the observable universe, called the extragalactic background light, and found that it is consistent with the galaxy counts. The total brightness of the sky outside our galaxy, summed across all wavelengths, matches what you would expect given roughly 170 billion to 2 trillion galaxies of known properties at various distances. This consistency check was one of the pieces of evidence suggesting the 2 trillion estimate from 2016 may be somewhat too high. The measured extragalactic background light appeared consistent with the lower end of the count range rather than the full 2 trillion. The debate continues, informed by this constraint alongside direct imaging data. The extragalactic background light measurement is itself a technical challenge. The sky is not simply the sum of galaxy light. It also contains the zodiacal light scattered by dust in the solar system, the diffuse glow of stars in the Milky Way's halo, and various instrumental contributions. Separating the genuine extragalactic contribution from all these other sources requires careful modeling, and different research teams using different methods have obtained somewhat different results. The New Horizons spacecraft, now far beyond the orbit of Pluto and therefore well clear of the solar system's dust that creates zodiacal light, was used to make an especially clean measurement of the cosmic background from a vantage point where the zodiacal contribution is minimal. Its measurements suggested the extragalactic background might be somewhat brighter than counts of individually detected galaxies can account for, implying there may be additional diffuse sources. Perhaps stars stripped from galaxies during mergers drifting through intergalactic space, or very faint galaxies too dim to be detected individually, contributing to the total. It is a reminder that even counting what appears to be directly measurable involves layers of complexity that are not obvious at first glance. 2 trillion is the headline, and headlines simplify. It is worth pausing to think about what the number actually contains, because each of those 2 trillion is not an abstraction. Each galaxy is a system of complexity on a scale that has no human equivalent. A large galaxy like the Milky Way contains between 150 and 300 billion individual stars. The uncertainty in our own galaxy's star count is itself remarkable, a product of the dust clouds obscuring our view of the galactic center. Each of those stars is a nuclear furnace, tens to hundreds of thousands of kilometers across, sustaining itself against gravitational collapse through the energy released by fusing hydrogen into helium in its core. Each star has almost certainly spent billions of years shining, cycling through its fuel, building heavier elements, and eventually distributing those elements back into space through stellar winds and supernova explosions. The most common kind of star in the universe is the red dwarf. Small, dim, and extraordinarily long-lived, burning so slowly that the most ancient of them will still be shining tens or hundreds of trillions of years from now, long after the sun has exhausted its fuel and dimmed to a cold white dwarf. Red dwarfs make up somewhere between 70 and 80% of all stars in the Milky Way. Their extraordinary longevity means they have had, or will have, far more time than a star like the Sun to host any worlds orbiting them. And the Milky Way, with its few hundred billion stars, is one of 2 trillion galaxies. Most of those stars have planets. The Kepler Space Telescope's survey of our galaxy confirmed that planets are extraordinarily common. The best estimates suggest that on average, each star in the Milky Way hosts at least 1 planet, and the most common type is a world somewhat larger than Earth, but smaller than Neptune. If that ratio holds across other galaxies, and there is no reason to think the Milky Way is anomalous, then the total number of planets in the observable universe runs to at least 10 to the 24th power. A trillion. The number of individual grains of sand on all of Earth's beaches combined is estimated at around 10 to the power of 18 to 10 to the power of 19. The number of planets in the observable universe exceeds that by a factor of roughly 1 million. Within that extraordinary population of planets, some fraction exist at distances from their host stars where liquid water could persist on the surface. Some fraction of those will have atmospheres. Some fraction of those will have the chemical conditions that appear, on the basis of our one example, to be potentially conducive to biology. The building blocks of organic chemistry, carbon, hydrogen, nitrogen, oxygen, the amino acids and sugars that underpin terrestrial life, have been found in interstellar gas clouds, in meteorites, and in comets. These ingredients are not rare. They are distributed through the observable universe in quantities broadly proportional to everything else that stars manufacture and disperse. What fraction of planets that meet these conditions actually produce life? And of those, what fraction eventually produce intelligence is completely unknown. We have one data point: Earth. And one data point is not enough to establish a rate, but the sheer scale of the available real estate means that even extraordinarily pessimistic assumptions about the likelihood of life produce, when multiplied against 10 to the 24th power planets, numbers that are hard to interpret as evidence for cosmic uniqueness. The silence of the universe, the absence so far of any confirmed signal from another technological civilization, remains one of the deepest puzzles in science. Perhaps more puzzling the better we understand how many places there are for life to exist. On timescales of tens of billions of years, the universe will look dramatically different from its current state. On timescales of trillions of years, it will be almost unrecognizable compared to the galaxy-rich panorama visible in today's deep field images. The accelerating expansion driven by dark energy will, over the next several tens of billions of years, carry all galaxies beyond the local group permanently outside our event horizon. The 2 trillion galaxies in today's observable universe will, one by one, recede beyond the threshold at which their future light can ever reach us again. The sky will not go completely dark. The galaxies of the local group, bound together by gravity that dark energy cannot overcome at those scales, will remain. But the rest, the tens of billions of galaxies visible in every direction when you look deeply enough, will be gone from view. Not destroyed, but simply beyond the reach of any communication forever. The pace of this recession is already measurable. Astronomers can calculate the distance at which a galaxy is currently receding from us so fast that light it emits today will never be able to close the gap and reach us. That threshold is already about 16 billion light years away. Galaxies beyond that distance are, right now, sending light toward us that will never arrive. They are emitting their history into a universe that will never receive it. And as dark energy continues to accelerate the expansion, that threshold will shrink over time, drawing closer to us and enclosing fewer and fewer galaxies within the circle of the observable. In 1 trillion years, a timescale so vast that it makes the current age of the universe look like an opening paragraph. An observer in whatever the Milky Way has become after its merger with Andromeda, and subsequent absorptions will look out at a universe containing, as far as any measurement can tell, only one galaxy. There will be no cosmic microwave background to detect, because the expansion will have stretched that radiation to wavelengths so long they fall below any practical threshold. There will be no spectral evidence of the dozens of other galaxy clusters and superclusters that populated our current sky. There will be nothing in the observable data available to that future observer to suggest that the universe was ever anything other than a single, isolated structure in an infinite void, unless detailed records from the current era have somehow been preserved across unimaginable timescales. This is not a reason for despair. It is a reason to recognize the remarkable accident of timing that places us in the current era, 13.8 billion years after the Big Bang, late enough for complex stars and planets and chemistry to have developed, but early enough that the full panorama of the cosmic web is still visible in every direction. We exist in what may be, from the perspective of any intelligent observers across all of time, a particularly privileged window for cosmology. The observations being made right now are recording a universe that will eventually be inaccessible. Every deep field image, every galaxy survey, every redshift catalog is adding to an archive of cosmic diversity that future eras will never be able to rebuild for themselves. There is a parallel shrinking happening on the stellar scale. As the universe's star formation rate continues to decline and the supply of cold gas is slowly exhausted, the total number of stars in the observable universe is also very gradually decreasing. New stars are still being born. The Milky Way adds a few solar masses of new stars per year, but the death rate of existing stars exceeds the birth rate on a cosmic average. The universe is not yet dying, but it has passed its peak. The most massive, most brilliant stars burn out in millions of years. The sun-like stars last billions. The red dwarfs will persist for trillions, but all of them will eventually exhaust their fuel. The 2 trillion galaxies we count today are, in a very long-term sense, slowly dimming systems, their stellar populations aging toward configurations that contain fewer young luminous stars and more quiet, ancient ones. The universe of 1 trillion years from now, fewer distinct galaxies, lower star formation, fainter and redder overall, is already foreshadowed in the trends that astronomical surveys measure today. On a clear night, far from the city, you can see the faint band of the Milky Way arching overhead. Hundreds of billions of stars, most individually invisible, their combined light blurring into that luminous mist that has fascinated human beings for as long as we have been capable of looking up and wondering what it was. The Milky Way is one. Just one of the 2 trillion estimated galaxies within the observable universe alone. Beyond the glowing arch of our home galaxy, the sky in every direction contains galaxies. Billions of them accessible to our current best instruments. Hundreds of billions more within the observable volume, but below current detection thresholds, and an unknown but possibly infinite number beyond the cosmological horizon. Most of them are invisible to the naked eye. Most of them will remain invisible even to the most powerful telescopes ever built. But they are there, distributed through the cosmic web, each one a vast system of stellar life at various stages of its history, each carrying its own population of stars, planets, and chemistry accumulated over billions of years. What the count represents, beyond its headline-grabbing enormity, is a hard-won accumulation of human understanding. A century ago, the Milky Way was the universe. 70 years ago, the best estimate was a few billion galaxies. 25 years ago, 100 billion. A decade ago, 2 trillion. Each jump reflects not an error corrected, but an instrument improved. A deeper look at a sky that rewards every increment of patience and precision with more structure, more depth, more history. The coming generation of instruments will narrow the uncertainties around that 2 trillion figure substantially. The Vera C. Rubin Observatory, now operational in Chile, is conducting a 10-year survey of the entire southern sky, building the most comprehensive statistical map of the galaxy population in the local and intermediate universe ever assembled, cataloging millions of galaxies, tracking large-scale structure, and detecting nearby faint dwarf galaxies missed by earlier surveys. The Nancy Grace Roman Space Telescope will add a wide-field infrared view of enormous sky areas, complementing Webb's extraordinary depth with breadth. The extremely large telescope, currently under construction in Chile with a primary mirror 39 meters across, will carry spectroscopy to galaxies far too faint for any current spectrograph, converting detected objects into understood ones. None of these will produce a final, unchanging number. The nature of the question makes that essentially impossible. There will always be galaxies below any given survey's detection limit. The definition of what counts as a galaxy shifts as fainter objects are found, and the observable universe is not a fixed container. But the direction of the history is clear. Each generation of astronomers, working at the limits of what their instruments allowed, produced the best answer possible. And each time the instruments improved, the answer got larger. The pattern is consistent. The message from the universe, every time we look more carefully, has been the same. There is something worth holding onto in that consistency. The 2 trillion figure is not the product of a single dramatic discovery like Hubble's Cepheid on a glass plate. It is the accumulated result of thousands of scientists across more than a century, building instruments, designing surveys, writing code, arguing about methodology, checking each other's work, and slowly assembling a picture of the sky that no single person could have built alone. The Hubble Space Telescope was operated by hundreds of people and used by thousands of scientists. The Constellus study drew on data from many different surveys conducted over decades at observatories on multiple continents. The James Webb Space Telescope is the product of contributions from engineers and scientists across 14 countries. The galaxy count is, in the most literal sense, a collective human achievement. And it sits alongside a fact that is easy to state but hard to fully absorb. Every one of those 2 trillion galaxies was there before any human being looked for it. Before any instrument was built to detect it. Before any theory existed to predict it. The universe did not wait for us to count it. It simply continued, vast and structured and largely indifferent, producing stars and planets and the chemistry of complexity at a rate and scale that makes the entire span of human civilization, impressive as it is, a barely perceptible flicker against the background. There are more galaxies than anyone previously thought, and the universe keeps insisting, every time we look, that the sky is not empty, that the darkness between the stars is not an absence but a depth, filled with structure and history and light that simply hasn't reached us yet. If that is the kind of thing that keeps you coming back, subscribe, and we will be here next time.